Deep beneath the snow on Ruapehu, the mountain begins to hum more strongly. The sound is too low for a skier to hear. Instruments feel it as a nearly continuous vibration. Then a large earthquake shakes the central North Island. It is natural to join the two events into one frightening story. Scientists did not. In August 2026, monitoring showed volcanic tremor at Ruapehu had risen from weak to moderate levels. The volcanic alert level stayed at 1. The nearby magnitude 5.9 earthquake was not identified as the cause. The useful idea is that a volcano is read as a pattern of signals, not as one alarm bell. Tremor matters, but its meaning comes from what the lake, gases, earthquakes, and ground are doing beside it. An ordinary earthquake often begins when rock suddenly slips on a fault. Energy is released in a break, followed by waves that travel through the ground. There is a clear event with a time, a location, and a magnitude. Volcanic tremor is different. It can continue for minutes, days, or longer. Moving gas, hot water, steam, or magma inside a volcanic system can keep the ground vibrating. The record can look more like a long band than a single sharp mark. That does not make tremor harmless. It makes it one clue. At Ruapehu, the increase began around July 22nd. That was before the larger earthquake near Taumarunui. Meanwhile, small earthquakes beneath the summit that had appeared earlier in the year seemed to have stopped by early July. The crater lake added another set of clues. Ty Amo sits over Ruapehu's active vent. For 4 months, its temperature had remained between about 18 and 23 degrees Celsius. Daily changes could come from sunlight, night, and weather, including snowfall. Scientists also saw persistent upwelling, sulfur on the lake, and a small overflow through the outlet. Volcanic gases told a similar story. The output of sulfur dioxide and hydrogen sulfide remained low to moderate, compared with long-term patterns. Put those observations together. The tremor had changed. The lake had not shown a matching rise in heat. Gas had not made a large jump. The combined picture still fitted minor volcanic unrest. That phrase has a precise place in New Zealand's alert system. The system has 6 levels, from 0 to 5. Level 0 means no volcanic unrest. Level 1 means minor volcanic unrest. Level 2 means moderate to heightened unrest. Levels 3, 4, and 5 describe minor, moderate, and major eruptions. The number describes the volcano's current state. It is not a countdown clock. The levels do not have to rise one by one, and an eruption can occur at any level because volcanic activity can change quickly. This distinction matters around Ruapehu. The mountain is not only a distant cone on a map, it holds ski fields, walking routes, roads, rivers, rail, farms, and towns within its wider hazard landscape. Different people need the same scientific information for different decisions. An aviation color code sits beside the public alert level. Pilots and airlines care especially about ash because it can damage aircraft engines. In the August bulletin, that color remained green while the public alert remained at level 1. Ruapehu's crater lake creates another danger, lahars. An eruption can throw lake water onto snow and ice, forming fast volcanic mud flows. The lake can also release water without a new eruption. New Zealand knows the consequence from Tangiwai. Ruapehu erupted in 1945. Over the following years, the crater filled with water behind a weak barrier of volcanic material and ice. On Christmas Eve in 1953, that barrier failed. A lahar traveled down the Wangehu River and destroyed part of the rail bridge at Tangiwai shortly before a passenger train arrived. 151 people died. The disaster changed monitoring and warning. Lahar warning devices were installed on rivers crossed by the railway, and a more advanced alarm network was added on the mountain in the early 2000s. That history explains why scientists watch a quiet lake so closely. Temperature, water level, chemistry, gas, and movement can each reveal a different part of the system below. That history gives a calm bulletin an important limit. It is not a promise of perfect prediction. Monitoring reduces uncertainty. It does not remove it. For people heading into Tongariro National Park, the practical habit is to check the latest volcanic bulletin and access advice before the trip. Conditions on a living mountain are not fixed by the date on an old article. The August 2026 tremor was real. So was the decision to leave the alert at level 1. Those facts do not pull in opposite directions. They show how the system is meant to work. Scientists notice a change, compare it with every other signal, and describe the whole mountain rather than the loudest line on one instrument. Ruapehu was humming. The job of monitoring was to decide what else, if anything, had joined the song.